We previously mentioned that the first ever fusion explosion requires the right moment of simultaneous happening of implosion and material encapsulation. From a state of 16 hydrogen molecules per cubic meter spread in the universe to the moment the first fusion explosion happens, 9 billion years would have passed. What happens when the implosion and the encapsulation do not appear simultaneously? Easily, heat generated in either case would escape, and temperature to ignite a nuclear reaction cannot reach. The continuous arrival of more materials only keeps the mass of the gathering growing. When the mass quantity presses certain threshold, an entity called a black hole appears. Black holes are a mass gathering of million or even billion times of the mass of our sun. To trigger the first fusion explosion, the mass quantity of that mass gathering is in the order of a few suns. But this mass of a few suns would have taken 9 billion years to come together. How many more times of 9 billion years for a black hole to reach its size? 90 billion years? 900 billion years? This can only mean that black holes exist far before the debut of the first explosion. And they lurk everywhere in the infinite universe within an unimaginable large distance from each other. It is said that not even photon can escape the gravitational grip of black holes. Possibly an expression closer to reality is that the gravitational grip is so deadly that even fusion explosions are powerless in the black hole. There is only one way to crack open the supreme gravitational predator. It is to let some material gathering collide some black holes at unmeasurable speed. When numerous layers and clusters of material gathering sweep through the space, some of them would sooner or later encounter with some of the black holes and drag them to move along. If a few more layers or clusters happen to join, a galaxy with several rotation arms will get into shape. A black hole, arrested by the rotation arms, in turn offers the gravitational hurting to stabilize the rotation. The way layers and clusters are born makes some of celestial objects move away faster from the ASP and some move slower. For those pioneering the moving away, they are going to enter a world of pure hydrogen clouds. Each of the pioneers may sooner or later trigger explosions that would induce the formation of clusters of layers centered on some point along their path. Then, as shown in the picture, launched by those pioneers far away from the ASP, some fragments from different clusters of layers would move in opposite direction. Someday, they may meet. When they meet, the scale of energy released by two giants moving in opposite direction is not what purely hydrogen explosion can compare. Besides, before the meeting, each of them are already in a state of hot plasma like our sun. When they clash at each other, their extraordinary dynamic and thermal states induce the birth of one object, a so-called quasar. The typical characteristics of a quasar include huge quantity of mass, extraordinary high speed of self-spinning, intensive heat, and illumination, and it usually has jet streams pointing away from it along the spinning axis of the quasar. The extremely energetic thermal activity makes the materials exist in a subatomic state, such as protons, neutrons, and electrons. Each particle just flies freely within the plasma. The protons are quickly designated to concentrate at the outskirts of the spinning bulk by the centrifugal force produced by the spinning and their own electrical repelling force toward each other. Unlike the protons, lacking the electrical repelling force, but with the mass compatible to protons, neutrons stealthily sink into the central region of the spinning bulk. They compactly stay together with supermass density. With respect to the center of the spinning bulk, starting with angular momentum similar to what the protons have, this supercompacted body of neutron ends up spinning at an extraordinary high rate at the center of the spinning bulk. Because of the electron's light weight, electrons may occupy space between the proton outskirts and the neutron core, or sometimes also appear at a space a little outside of the proton outskirts, depending on the spinning direction of the compact neutron core. Neutron stars are usually strong magnets. Therefore, the neutron core of the quasar must carry a strong magnetic field. If the quasar spins at a direction as indicated, like the quasar disk in our picture, the neutron core that must spin faster than the proton outskirts will force some protons to move to the center region of the quasar, while at the same time force some electrons to stay further away from the central region. Then, the quasar would make the central region a field with more positive electrical potential. When a proton, or any particle with positive charge, is forced to enter this central region by the rotating magnetic field, it must experience a strong repelling force. Besides, when it gets very close to the spinning axis, the particle loses all mechanical potential to stay out of place with balance allowed by mechanical forces, such as the sum of gravitational force and centrifugal force. Then, the positive particle is exclusively ejected. All those ejected come together, forming a jet stream. So naturally, the particles so ejected, and thus the jet stream so formed, would move on the line of the spinning axis of the quasar. With more protons or other positive particles having departed from the quasar, excessive electrons will evaporate from the quasar. Gradually, more and more loss of mass will bring the quasar to meet its day of disappearance, leaving only its neutron core to witness the historical location of the bygone quasar. Of course, the original spinning direction of the quasar may also have been opposite of what we present above. In this case, a field of negative potential would hover over the central region of the quasar, and the jet stream would consist of particles of negative charges. Because of the light weight of electrons, its movement would agitate the electromagnetic waves of higher frequency in the optic spectrum, such as an X-ray. Comparison of the orientation of the fragments of layers between two clusters shows that many of them are perpendicular to each other before the two clusters permeates each other. When the permeation happens, all these perpendicular fragments serve as the base to cause a web-like appearance for the overall material distribution. A web would bring up two concepts, knot and filament. Furthermore, many of the fragments may also collide at each other head-on, bringing up the appearance of some unusually prominent cosmic organization that also appears as filament.